Um, Thank you so much. This is our fourth lesson on radioactivity. And just in case you've not been able to go through the rest, you can still look at them. I've labeled them as lesson 1, lesson 2, lesson 3. So this is the fourth lesson that you're having on radioactivity. And it is a continuation on the detectors. The previous lesson talked about the other detectors. And in this lesson, I'm going to talk about the GM, or rather the Geiger-Muller tube. So straight for the business of the day. The GM tube appears as it is drawn there. That is the GM tube. So I want us to note the parts that are there on the GM tube. We have the Mica window. This is the Mica window, and it is supposed to be made to be what? Thin, because the radioactive substance is normally placed at this point so that when it releases the radiations penetrate through the Mica window. So in case this window is made to be thick, it will block some of the radiations. So to ensure that the radiations passes through very fast, then it is required that this window should be thin. Then within the tube, we have gas at low pressure. That is the argon gas with a little bromine. We have the aluminum tube, that is the cathode. We have a battery here. We have a fixed resistor here and a pulse counter. This is where the counts will be registered. So this is what happens, and I've explained that in the notes. On the right-hand side of this screen, when you have a radiation here, this Mica window allows the passage of radiations, and the radiations, while in the tube, the radiations ionize the argon gas, sorry. So when argon gas is ionized, it results into two ions, the positive and the negative ones. The negative ones will be attracted to the anode and they'll cause a current to flow. And then when a current flows, there are some counts that will be registered on the pulse counter. So when we have some count on the pulse counter, that is a clear indication that the source that is placed here is actually radioactive in nature. Just in case they place a source that is not radioactive before I go to that, sometimes you will notice that when an experiment is being carried out by the GM tube, sometimes even before a source is placed here, a radioactive source is placed here, there are some counts that are already registered on what? The pulse counter. Such counts are actually known as the background counts, and they result from background radiations. And later on, I'll explain something to do with background radiation. But if there are no background radiations and they happen to place a source that is not radioactive before the Mica window, what will happen is that there will be nothing registered on the pulse counter. Within the GM tube, you can also notice that they use some bromine gas, a little bromine. The bromine gas acts as a quenching agent. What does it imply? I've mentioned that when you have radiations entering the Mica window, and these radiations reach in here, they ionize the argon gas. So when argon gas is ionized, it results into two ions, positive and negative ones. The negative ions are attracted to the anode and they cause a current to do what? To flow. The positive ones are supposed to move to the aluminum tube, but there is a problem. If these positive ions reaches the cathode, they can lead into more ionization, which will register a wrong what? A wrong current, or rather a false current or a false count, because we are looking at the effect of the radiation ionizing the air. So any other ionization happening here can lead to the Don't know what has happened. Sorry. I'll stop the sharing and share again. Sorry for that. So they lead to the registering of false what current. So to avoid all these, bromine gas is normally provided so that the bromine gas will absorb the kinetic energy of the positive ion so that they don't reach the cathode. So what are the background radiations? I've just mentioned something about the background radiations. Background radiations, these are radiations that are registered or observed in the absence of a radioactive source. And the count registered in the absence of a radioactive source is referred to as the background count. What are the sources of these background radiations? The sources of the background radiations include and not limited to cosmic rays from outer space, radiations from the sun, some rocks which contain some traces of radioactive materials, e.g. granite, and natural and artificial radioisotopes. So those are the four sources of the background radiations. Then we have the decay curve. I've mentioned that whenever you have a radioactive material such as cobalt-60, you realize that this material will disintegrate. So as it disintegrates, it releases some radiations. And some of these radiations have a mass. So what does it imply? The size, the mass of the radioactive substance is expected to reduce with time. As it continues to disintegrate, the size does what? Reduces. For instance, before you, we have the decay curve for cobalt-60. That during the start, the mass of this cobalt-60 was 100, but within 1 year, it had reduced from 100 to 50. And then within the second year, it reduced from 50 to 25. And then within the third year, it reduced from 25 to 12.5. I want you to note something. When the mass was 100, it took the cobalt-60 for its mass to reduce from 100 to a half of 100, that is 50, in 1 year. Then when it was 50, a half of 50 is 25. It took 1 year for the mass to reduce from 50 to 25. So there is a special name given to this duration that it takes a radioactive substance for its nuclides to reduce to half the original number. And this term, the time is specifically referred to as the half-life. So half-life is the time taken for radioactive substance for its nuclei to reduce from half the number of the original what? Nuclides. Have explained this in our next slide. Half-life is the time taken for half the number of nuclides initially present in a radioactive sample to do what? To decay. And again, you must have noted that from this decay curve, when the mass is 100, within 1 year, 50, the mass that undergoes disintegration is what? 50. If the mass reduces to 50, only 25 grams does what? Disintegrates, implying that the more the mass, the higher the rate of disintegration. Or simply, the more the nuclides, the higher the number of disintegrations, the higher the rate of disintegration. So the disintegration that occurs for any radioactive substance depends on the number of nuclides present. If the nuclides are many, then the rate is high. If the nuclides are fewer, then the rate is low. And that can be summarized in what we refer to as the decay law. And this is what the law says. It states that the rate of disintegration at a given time is directly proportional to the number of nuclides present at that time. So I've already explained the graph below that if you're having a certain radioactive material, and the amount of the radioactive material initially is what? A naught. After a half-life, this will reduce by a half. After the second half-life, it reduces by another half. And then the same way. So it was initially A naught. After the first half-life, it comes to A naught over 2. After the second half-life, it is A naught over 4. That is A naught over 2 multiplied by a half. And then after the third half-life, it will be A naught over 8. I've already mentioned that. So there are some calculations that can be done for radioactivity using the decay formula. And that is the decay formula. N is equivalent to N naught, a half, the power of capital T over small t, where, be attentive because I think I've interchanged something here, where N is the remaining count rate and N naught is the original count rate, sorry. And then T is the total time of decay and small t is the half-life. So you're going to use this formula in some examples. And apart from this formula, there are some other ways in which you can approach the same question. So that is our first example. For a certain radioactive material, the average count rate is found to be 82 counts per second. And I want you to have a pen and a piece of paper so that we can do these calculations together. For a certain radioactive material, the average count rate is found to be 82 counts per second. After a time of 210 seconds, the count rate had dropped 19 to 19 counts per second. The average background count rate remained constant at 10 counts per second. What is the half-life of the material? So this is a question in which, apart from being given the counts per second, the question is also giving us the background count rate. So for the 82 provided there, which is the count rate at this beginning of this experiment, still consists 10 counts per second from the background radiation. So when you're carrying out such a question, the first thing you're supposed to do is to subtract the 10 background count rate from 82 to get a 72. So if the number of half-lives drops from 72 to 9, the number of half-lives drops from 72 to 9, then it implies that there were several half-lives from 72 to 9. Because we have the first half-life when the mass, the counts drop from 72 to 36. That is our first half-life. Then the second half-life, when the mass drops from 36 to 18. Then the third one from 18 to 9. So within the 210 seconds, how many half-lives are we having? There are 3. So for you to be able to know the duration of a half-life, you will take the 210, divide by 3, which gives you 70 seconds, and 70 seconds is the half-life. Then, let's continue. Then, if we are to use the formula that we had above, then our N will be 9. I want you to do that substitution very fast. Our N will be 9. That is the remaining count rate, which is equivalent to N naught. Our N naught, the original one, was 72. So 9 is equivalent to 72. Then a half power of 210 over T. Very fast mathematics. 9 is equivalent to 72. A half 210 over T. And come up with the value for T. And you will notice that T is equivalent to the same answer as the one here, which is 70 seconds. So it is your work, you as a learner, to choose on a method that will be suitable for you. You can choose this one, which looks simpler for me, or you can use the formula. And then another example here, the graph below shows a decay curve of a radioactive material. Use the graph to find the half-life. The graph below shows a decay curve of a radioactive material. Use the graph to find the half-life. So the graph is the graph of number of counts against time. So the counts at initially 120, but because this substance is decaying, then it means that this number of counts will reduce with time. So for us to be able to get the half-life from this graph, we need to know what is a half of 120. And a half of 120 is 60. So find out from 120 up to 60, what was the time? How much time did it take for the counts to reduce from 120 to 60? So we can draw a horizontal line at 60 to meet this curve, then drop up a line here to meet the time scale. And you notice that the half-life is actually 30 seconds. 30 seconds. Do as many examples as possible. And in case of a question, a clarification that you need, you can write that in the comment section, and I'll surely respond to it. Applications of radioactivity. I don't know if we have much time. Applications of radioactivity. One of the applications of radioactivity is used in carbon dating. Radioactivity is used in carbon dating. C14 is made by the action of cosmic rays. Life is based on carbon. When least organisms are alive, C14 will be absorbed at the same rate as what? C12. So sisi wenye tunaishi, we absorb some carbon. We absorb some carbon from the cosmic rays, and this carbon that is absorbed from the cosmic rays is C14. But on dying, the C14 will no longer be absorbed. So it will undergo decay. C14 undergoes decay after we do what? We die. So when it undergoes decay, and we have archaeologists that are trying to find out what is the age of a certain fossil, they simply need just to measure the C14 in our bones, maybe the C14 in our hairs, or C14 in the wood, so that they are able to date the fossils. You remember, like in Form 1 history, I think under the early man, we talked about the Dryopithecus, the Ramapithecus, and the ages were being given. These archaeologists were able to come up with that age when they measured the amount of C14 within the bones. Apart from that, sometimes someone can die, especially these people that die and then their bodies are found some days after their death. What the archaeologists do, they only do what? They only measure, they're called the forensic scientists. They only measure the C14 within these people's body and then compare it with what? C12, and they are able to tell at what time did this person die. They're able to estimate the exact time that a certain abandoned body actually died. Then we can also have the gamma rays being used in medicine. Gamma rays, just like X-rays, are used in the control of cancerous body growth. The radiation kills cancer cells when the tumor is subjected to it. Gamma rays are also used in the sterilization of medical equipment and for keeping pests or making them sterile. The other application is for detecting pipe bursts. Underground pipes carrying water or oil may suffer bursts or leakages. If the water or oil is mixed with some radioactive substances from the source, the mixture will seep out where there is an opening. If a detector is passed on the ground near the area, the radiations would then be done what? Detected. So our lesson ends there. I'll do another lesson, that is lesson number 5, that will finish up on the other applications of radioactivity, and I'll also handle the nuclear fission and fusion.